Hi everyone, can you hear me? Hi everyone, hello Vijay. Hi Rohit, how are you all? Let me know if you can hear me and then we will be starting, right? Okay, so let's get started. Today we are just going to cover few more PYQs that we have left last time. So this session will be about the PYQs only. So we will be covering more PYQs that we have left last time. Let's get started. So let me start with the first PYQ. So before that, I just want to tell you that these are the videos that I already have for the algorithm. So if you want to watch the algorithm, then just watch these of the videos because these are really nice videos. Okay, cool. So let's get started with our data structures PYQ. So let's solve this PYQ. Now, what this is saying, let's see what this is saying. It is saying that derive a recurrence relation for the size of the smallest AVL tree with height h. Okay, so they want to derive a recurrence relation for the smallest AVL tree of height h. That is the question. Now, what does this mean? Let's just solve it for the smallest and for the biggest, and then you will get to know that what does this mean, right? Good. So let's just continue. Now let's just see that what's going to happen if your AVL tree is having the smallest size. What do I mean by that? AVL tree, let's suppose this is a AVL tree which is having two, I mean this is a root which is having two subtrees. Okay. Now if it is having two subtrees, in this case, what you will say that if the AVL tree height is h, then can you tell me what should be the height of these two subtrees? The height h is possible only when like one of them have to have the height h minus 1. This could be h minus 2 also or h minus 1 also. So this is one possibility, which means one of the subtree must be having height h minus 1. So this is another possibility, right? Where this is h minus 1 and this is h minus 2 or vice versa, right? But tell me if this is a possibility where both of them are having h minus 2 height. If both of them are having h minus 2 height, then what will happen? Then you will say that if both of them are having h minus 2 height, then the ultimately this height will not be h, right? It will be lesser than h. Let me know if that is clear to everyone. Cool. So I hope you understood this, right? Now, so what do I mean by that? It means that if you want to have a AVL tree, then there are a couple of options that you have. One option is that you can have these two subtrees are there. You can have the heights h minus 1, h minus 1, or h minus 1, h minus 2, or maybe h minus 2 and h minus 1, but both of them cannot have height h minus 2, right? Now suppose I want to design an AVL tree with height h such that I have maximum number of nodes. Okay, so suppose we want to have an AVL tree with height h such that we have maximum number of nodes within height h. Tell me what you should be doing in this case. If I just ask you this, then what is your answer? You will say that if there is a height h, in that height h, if you want to have maximum number of nodes, then what you need to do, each level should be full, right? Each level should be full. So I will be making each level full. So each level I will be making full, and then finally I will be having an AVL tree which is like this. Basically each level will be full here, right? So each level will be full, right? Each level is full, and finally I might be having something like this. So what is the maximum number of nodes that you can have within height h? You will say that this is the height h, means this is 0, this is 1, this is 2, and this is height 1, height 2. I think this will be height h, right? This is height 1, 2, yeah, this will be height h. So you will say that the total number of nodes that you have here is 2 power 0, because at 0th level, at first level you have 2 power 1, at second level you have 2 power 2 nodes. Similarly, if you keep on doing it, then at s level you have 2 power h nodes, and finally you will be having something like this, right? So which is basically 2 power h plus 1 minus 1. So this is the maximum number of nodes that you can have in an AVL tree of height h. This is the maximum number of nodes in AVL tree of height h. Now let's just see if we can do it using a recurrence, which means I want to drive a maximum number of nodes in an AVL tree of height h, but let's just see if we can do it using the recurrence. Okay. So what do you mean by that? Let's just see. So what I'm saying here is that suppose you have an AVL tree. Now what I want to have, suppose this AVL tree is having height h, then I want to have the maximum number of nodes, right? If I want to have a maximum number of nodes in this AVL tree of height h, now tell me, if it is to me, like I mean if it is given to me that I can have I can have any height, I mean there were a couple of options that I were having here. It is h minus 1, it is h minus 2, or maybe h minus 1, h minus 1, and maybe it is h minus 2, it is h minus 1. Let's suppose these three options I have here. Okay, this is option A, option B, option C, which means I can have this height as h minus 1, this height as h minus 2, or maybe this height as h minus 1, this height as h minus 2, something like this, right? So let's suppose these three options that I have. If I want the maximum height, then tell me which option you will be picking, which option you will say is best suitable for you. Okay, so maybe I can just minimize my window. Okay, now I hope it is visible to everyone. Now tell me which option will be best to you. If there are a couple of options, yeah, so you will say that the option which is having the higher height, so which means if you want to have, then you will be having this option B, right? Because it is having h minus 1 at both the places, so that's why you will be having h minus 1 height here, h minus 1 height here, because you want to have the maximum height so that you can put the maximum number of nodes, right? So this is h minus 1 could be the maximum height here, h minus 1 could be the maximum height here. So that's why if you want to have the maximum number of nodes in this AVL tree, then you will be saying that this height should be h minus 1, this height should be h minus 1. So finally you come up with the idea where you are saying that if nh, let's suppose nh denotes the maximum number of nodes, maximum number of nodes in AVL tree of height h, tree of height h, then can you write this nh recursively? So see, if you want if you want to have the maximum number of nodes in this AVL tree of height h, then you should be having the maximum number of nodes here. You should be having maximum number of nodes here, right? You fix the height, that is okay, but you also want to have the maximum number of nodes here, maximum number of nodes here. So which means you will say here the number of nodes that could be maximum is n h minus 1. Here the number of nodes that could be maximum will be n h minus 1. And then finally you will say that see, if the height is h minus 1, then I am having the maximum number of nodes I can have nh minus 1. Why? Because if height is h, because that's what I defined, right? That's what I defined, and I want to actually calculate it. I want to calculate this nh. So if nh is maximum number of nodes in height h, then I will say that nh minus 1 is maximum number of nodes in height h minus 1. Nh minus 1 is maximum number of nodes in height h minus 1, right? So basically I will say that this nh which I am defining, right? This nh which I am defining will be equal to n h minus 1, the number of nodes here, plus the number of nodes in right subtree, plus 1 is the root, right? So this is how you can define your recurrence. And obviously there will be a base case. If height is 0, then there is a number of node is just 1, right? If height is 0 and 0 is just 1. If height is 1, then maximum number of nodes maybe you can define, or maybe you can calculate using this also. Then the maximum number of nodes will be 3 if height is 1. I hope that is fine to everyone. So finally we come up with nh, which is looking like this, where nh is the maximum number of nodes of height h, right? nh minus 1 plus nh minus 1 plus 1, right? 1 is because of the root, this nh minus 1 is because of the left subtree, this nh minus 1 is because of the right subtree, right? Now let's just simplify it. This is 2 into nh minus 1 plus 1, which is nh, and this is the recurrence I am getting. If you just simplify this recurrence, I mean if you just unroll this recurrence, you will be getting nh equal to 2 into this nh minus 1. You will say that you can again do it, which means 2 into 2 into nh minus 2 plus 1, and then this plus 1 is already there, so plus 1, right? So that's how you can unroll this, which means you can put the value of nh minus 1 here, which is 2 into nh minus 2 plus 1. Now if you unroll this, this will be 2 square into nh minus 2 plus 2 plus 1, right? Now if you do it k times, like you just did it 1 or 2 times, if you do it k times, you see the pattern. It is 2 power k into nh minus k plus, if you are doing see, this 2 and this 2 is matching, which means plus k minus 1, like that, right? Till 1, it will be till 1, k minus 2 till 1. So if you want to solve it, then let's just quickly do it. What will the answer here? Let's just see. Okay, so it will be, I think if you put k equal to h, it will be 2 power h n0 plus, is this right or there is something wrong? Okay, I think it will be h plus h minus 1. Maybe let me just see if I can do it, if I can just unroll it one more time, and let's just see the pattern that we are getting. Okay, so if you unroll it one more time, then you will be getting 2 square into, what is nh minus 2 here? nh minus 2 will be 2 into nh minus 3 plus 1, 2 into nh minus 3 plus 1, and then plus 2 plus 1. Yeah, so you are getting this series, which is 2 cube nh minus 3 plus 2 square plus 2 plus 1, right? So finally what series you will be getting? Let's just write it. So finally you will be getting something like this, which will be, in terms of 2 power k, it will be 2 power k into nh minus k plus, it will be 2 power k minus 1 plus 2 power k minus 2, 2 power 0 or 2 power 1, right? 2 power 0 or 1, so both are same. So if you put h equal to, or k equal to h, then you will be getting 2 power h into n0 plus 2 power h minus 1 plus 2 power h minus 2 till 2 power 0, and n0 is 1, that is our base case. And finally you will be getting the same answer that you have got earlier, which is 2 power h plus 1 minus 1 upon 2 minus 1, which is also equal to, right? Finally you are getting the same answer that we have got earlier. So basically this thing you have got, which is also equal to 2 power h plus 1 minus 1, right? So this is the same answer that we have got earlier. Let me just show you that that we have earlier also got the same answer. See, earlier if you have done this without using the recursion, then also you got the same answer, which is 2 power h plus 1 minus 1, and now also you got the same answer, right? So both answers are actually same. Yes, both answers are actually same. Now either you do it using recursion or you do not using using recursion. That is up to you. I mean, for the maximum, that's how we are getting, right? Now let's just try doing it for the minimum. Okay, which means let me just see that what is the minimum number of nodes. What is the minimum number of nodes in an AVL tree of height h, right? See, for the minimum number of nodes, let's suppose you want to have height 0, obviously that's the compulsory. If you want to have height 1, then you do not need to have these two nodes, right? What you can do for the minimum, what you can do, you can just have one of the node, maybe this, right? This is also the AVL tree of the height 1, right? This is also the AVL tree of the height 1. This is also the AVL tree of the height 1. These are the three AVL trees of the height 1. Out of them, two are having the minimum number of nodes, right? This is having the minimum number of nodes, this is having the minimum number of nodes, and this so happens to have the maximum number of nodes. Now these are the AVL trees of height 1. Now let me tell you how many AVL trees are there of height 2. So for height 2, maybe, okay, you cannot have like something like this, so that's why you need to have something like this, right? So this is AVL tree for height 2. Now you can append this anywhere, maybe here, something like this, which means that there are a couple of possibilities for this, right? I mean, this structure is fixed, and then there are a couple of possibilities just for this sibling, right? I mean, you can append this anywhere, maybe at this left or right, or this left or right. So these are the AVL trees of height 2, but there are more, right? There are more. You can have these two also. Similarly, you can have here also. So there are many more AVL trees of height 2. Out of them, you will say that this is having minimum number of nodes, this is minimum, this is minimum, this is minimum, this is having maximum number of nodes. And there are some AVL trees which are like this, which are having neither minimum nor maximum. This is an AVL tree of height 2, which is not having the minimum number of nodes, or neither it is having the maximum number of nodes, right? So this is the AVL tree of height 2, which is not having minimum or not having maximum. Okay. So I want to, I don't want to count it. Okay. I don't want to count it. I just want to have the number of nodes in my place, right? Which means how many number of nodes are possible in an AVL tree of height h. Minimum number of nodes. Minimum number of nodes in an AVL tree of height h. This is what I want to calculate. Now, suppose as I just told you that I mean, if you are having height 1, then the minimum number of nodes are basically 2, right? These are the minimum number of nodes. If you are having height 2, then this is 1, 2, 3, and then 4 is the minimum number of nodes. So similarly, I want to calculate the minimum number of nodes for a general height, which is h, right? For a general height h, I want to calculate my answer. Let me know if you have understood this or there is some confusion here. Okay, okay. So I hope you understood. Now let's just continue. So let's suppose again this NH. Okay, this NH is different from that NH. I can use a different notation if you want to. I can use MH also, which is the minimum number of nodes. For the minimum, I can use M. But I think you will get confused because this M is for minimum or maximum, something like that, right? So maybe let me just use the same notation, which is NH. But here this NH is the minimum number of nodes. Minimum number of nodes in an AVL tree of height h, right? Now let's just calculate this NH. Now tell me, if I have couple of options here, which means if I have these options to put the height, so this height is h. If I have this h minus 1, h minus 1 option, or maybe one of them is h minus 2 or another one is h minus 1, which one I will pick? If I want to have minimum number of nodes, then let me know which one I will pick. Okay, so see, if you want to have minimum number of nodes, then you must be picking minimum everywhere, right? So you must be saying that okay, this kind of combination looks good to you. Reason being is that because here you are having one of them is h minus 2, another one is h minus 1. If you try to do both of them h minus 2, then it is not possible because the ultimately height will be then h minus 1, right? But your height should be h. That's why ultimately you want the height h, so h minus 2 is not possible. So that's why you will say that you are having I mean, this combination looks good to you, right? So which means one of the subtree should be having the height h minus 2, one of them should be having height h minus 1. So this combination is looking good, so which is fine. Now let's just see how to do it. That is fine. Now let's just see how to do it for the counting, which means how to count the minimum number of nodes in an AVL tree of height h. So NH is minimum number of nodes in an AVL tree of height h, right? That's what I have defined as NH. So maybe I can just copy this NH. Now see, if you want the minimum number of nodes, then obviously you should be having the minimum number of nodes everywhere. Recursively you will be having, right? So these are the heights, but you should be having the minimum number of nodes here also. You should be having the minimum number of nodes here also, which means you will say the minimum number of nodes of height h is, if that is the NH, then the minimum number of nodes of height h minus 2, it is NH minus 2, and here it is NH minus 1, right? So that's why the minimum number of nodes in height h will be NH minus 2 plus NH minus 1, and then this will be the root, which will be plus 1. So that's how you can calculate the minimum number of nodes. Now you can have the base case. If height is 0, then obviously 1. If height is 1, then there you just need 2 nodes, right? Then this is 2, and I think this base case will be fine, right? Okay. For n2 you can calculate, like so for n2 if you want to calculate, you can calculate using this formula. So let me show you some of the calculation. So this is your base case where n0 is just 1, n1 is 2, and now your in general your nh which is greater than equal to 2, for the greater than equal to 2, you will be having nh minus 1 plus nh minus 2 plus 1. So earlier, if you remember, we have unrolled it and then we have found out that what should be the final answer, right? We have unrolled this and then we have found out that what should be the final answer. But here, the thing is that, like, I mean, if you try to find the final answer, that will be quite complicated. I mean, that's not straightforward. This is just like a Fibonacci series. If you can recall the Fibonacci series, then this is just like a Fibonacci series. This term plus this term, but this one is extra. I mean, in Fibonacci, the one is not extra, but here this one is extra. Anyway, let me not unroll it because it will be messy and there is no closed form solution. Closed form means that there is no final formula that you will be getting. Earlier we have got this as a final formula, but here we might not get a final formula. So that's why I'm not doing it. Okay. But let's just do it for the sake of practice. What will the n2? N2 means minimum number of nodes for the height 2. It will be n1 plus n0 plus 1, which will be n1 plus n0 plus 1, which means this is 1 plus 2, 3 plus 1, 4, right? It will be 4. So basically the series is something like this. So I can say n0 is 1, n1 is 2, and then n2 is 4, right? So this is 1, this is 2, and then finally it is 4. So this is the series that I'm getting. Can you guess this number? What should be this number? See, the number should be sum of these two previous plus 1. So basically it should be 6 plus 1, which is 7, right? And then if I just ask you to guess this one, then you will say 7 plus, I mean, this is for 0, this is for 1, this is for 2, this is for 3. If I just ask you for this, then you will say 7 plus 4, 11 plus 1, this is going to be 12. Then 12 plus 7, which is 19, then this is going to be 20. 20 plus 13, which is 20 plus 12, which is 32, then you will be getting 33. 33 plus 20, it is 53, and then you will be getting 54, something like this, right? This is 4, this is 5, 6, 7. And I think in the question, what they have asked is, like in the question they have asked for the minimum number of nodes in an AVL tree. Okay, they have asked for the general recurrence and what is the size of the smallest AVL tree with the height h. So they are asking for the height h, which means for the height 7, this is the answer. For the height h, it is 54 plus 33, which is 7, 8, 87 plus 1, which is 88. 88 is the answer for the height h, right? Minimum number of nodes is 88 for the height h. Let me know if you have understood this particular question. Okay, cool. I hope you understood this. So 88 should be the answer. Let me check the answers also. Yeah, 88 is the answer, right? So that's how we can calculate the minimum number of nodes and also the maximum number of nodes. If we just notice that for the maximum, the answer was 2 power h plus 1 minus 1. So this is for the minimum, but let me write the corresponding maximum. For the maximum, height 0 means 1 only. Height 1 means you will be having these 3 nodes, right? Height 1 means 3. And here you will be getting height 2 means 2 power 3, which is 8 minus 1, 7. Height 3 means 15. This should be 31, and then okay, 32 and 64, which is 63. Then 128, which means 127 here, and then this is 511. Then this is 1023, something like this, right? Now you see the difference here. See, if you want to have height 8, then the minimum you just need 88, but the maximum for the height 8 is 1023, right? So these are the minimum for height 8, these are maximum for height 8. And similarly for height 6, if I talk about, then this is the minimum. For height 6, you need to have minimum how many nodes? Minimum 33 nodes you need to have, and maximum how many can you can have? Maximum you can have 127, right? Okay. Now tell me if I just ask you the reverse question, that if I just say the number of nodes are 34, then what will the height? Height is still 6. Why? Because I mean the maximum height could be still 6. Reason being is that for the height for the height 5, sorry, yeah, for the height 7, you need minimum 54 nodes, right? You need minimum 54 nodes for the height 7. So if you have 33, then height is 6. Even if you have 34, then also height is maximum height can go to 6. If it is 35, then the maximum height can go to 6, right? Minimum height could be very less. See, with the 33, the minimum height could be just 5. Okay, you might be getting confused, so let me not do it. Maybe you get confused. But I hope you got this recurrence and you will be able to solve the question using these recurrence if you have understood the thing that what I am talking about, right? So minimum these many nodes, maximum these many nodes. So if you go on further, this the difference is actually getting larger and larger, right? Earlier you think that okay, this is almost same, almost same, almost same, almost same, almost okay, this is not same, this is 54 and 511. Then 88 and 1023, huge difference between the minimum and the maximum, right? That's how quickly these things are changing. Cool. Let's move further. Now, let's solve this question. What they have asked is that a data structure required for storing a set of integers such that each of the following operation can be done in order of log n time. So they are looking for the data structure such that each of the following operation that they are talking about, right, that can be done in order of log n time. So now let's just see that which data structure can do them, can do the task for them. So this deletion of the smallest element should be done in log n time, and insertion of an element if it is not already present in the set, and that should also be done in log n time, right? So deletion should also, deletion of the smallest if they have the two requirement, and both of the requirements should be filled in order of log n. Order of log n means maximum it can go log n, but it should not go beyond log n, right? This is what order of log n means. Now, what the second line is saying is very interesting. They are saying insertion of an element if it is not already present, right? So if you want to insert some element, then the second line can be broken into two tasks. You first have to check, is this present? Okay, which means if you want to insert something, then you first check, is this already there? Is this element present? Something like this. You need to check, is this element present? If your answer is yes, if it is present, then you do not insert. If your answer is no, then you insert, right? Don't insert. So this complete task should be done in log n time. That's what they are saying, that insertion of an element if it is not already present in the set, then you should be doing in log n time, which means that this complete thing you should also be checking whether it is present or it is not present. Okay, 255 I have missed. Cool, no problem. Yeah, 255 I have missed. So here, this is 255 and 511. Cool. Thank you for telling me. This is 255 and then this is 511. Okay. Right. So I hope you understood. Now, this element could be any arbitrary element. If you want to insert any arbitrary element, then it should be done. It should be done in log n time. Okay. You first be checking whether it is present or not, and then you will be inserting it. Now tell me, can you do this using a heap? A heap can be used, but not a balanced binary search tree. Can you do this using a heap? No, right? See, you can delete the smallest element from the heap in log n. That is fine, but you cannot insert an element. I mean, you cannot basically have this check. Okay, you cannot have this check in the heap whether it is present or not in the log n time, because in the heap there is no system. Heap is not made for the made to search the keys, basically you can say, right? Heap is not made to search the keys. I mean, there are different purposes for heap. It is generally for the priority queue. I mean, it is generally for the finding the smallest or maximum. So but it is not to search the keys. It is not made to search the keys. So if you want to search any key in the heap, then it might take order of n to search a key in heap, because there is no system, right? In heap there is no systematic way, the way we have arranged the heap. I'm just saying that this top is minimum. Let's suppose, okay, I'm just saying this top is minimum. Then I will say that okay, apart from that I can have some couple of more things, that okay, that maybe second minimum could be here, third minimum could be anywhere. So if the number is, let's suppose anything, maybe if I say that number is some random number, then I don't know that where is this number present, right? In general, if the number is, let's suppose, maximum, it could be anything, right? It could be here also. So I don't know the where is this number present. So that is why they will take order of n. Heap will take order of n. So the second task I cannot do using a heap, just because the reason why I cannot do, because I cannot search in the heap in just order of n time or order of log n time. So a heap cannot be used for sure. A balanced binary tree can be used but not heap. Yeah, that's the answer. Because in the balanced binary search tree, which is just like AVL tree, the height is log n, right? If the height is log n, then you can definitely you can definitely delete the smallest, or you can find any number in the log n time, right? Because in that AVL tree, smallest will be found at the leftmost, right? If you want to delete it, you can definitely delete it. Okay, I mean in the log n time you can definitely delete it, right? So at most what will happen in an AVL tree, like it will look like this. For the minimum you will be finding here, then the height is log n. So at most it can have the right children, maybe you can say one. Okay, it cannot even have one more, right? Because if the moment it has one more, the balance factor for this is not satisfied. So at most it can have one more right children. Anyway, like you can definitely delete this element in log n time in an AVL tree. And similarly, you can find any element in an AVL tree in log n time. So this check can be done in log n time, and then you can insert or not insert. Based on that, you can take another time, right? So it can be done in log n time. So that's why that balance binary search tree can be used but not heap. Okay. Uh, so let me just check the doubts. So for finding the minimum nodes in an AVL tree, why it is wrong? Which one? Fill h minus 1 height, fill maximum, then plus 1 for h. Okay, let me first explain this question properly. So I think this question is done, right? So are you convinced with this question? So this question is having B as an answer. So there are some doubts in previous question. So I will just check it. So answer is B here. Okay. So here I hope that is done. Now let's just go to this particular recurrence. So I think there are some doubts in this recurrence that people are having. Okay. So let me just try to solve those doubts. Okay. So what are your doubts? Let me just take those doubts here. So this is the doubt. Rohit is saying that for finding the minimum nodes in AVL tree, why it is wrong? Fill h minus 1 height with maximum nodes, then plus 1. No, you want to, if you fill this with maximum node, that's the problem, right? I mean, you want minimum everywhere, not just a minimum. I mean, this h minus 1 is saying that you should be having height h minus 1 here, height h minus 2 here, and then recursively you should be having the minimum, right? It's not like that. Okay, for this particular node you are having minimum or something, right? You should be having the minimum recursively. Recursively means here, if given a chance, you want to have the minimum number of nodes here also, right? If given a chance, you want to have minimum number of nodes here, you want to have minimum number of nodes here. If the total minimum number of nodes in height h, I'm saying nh, then this will be nh minus 2, this will be nh minus 1. Suppose my question is something like this. My question is something like this, that this is an AVL tree that I want to have. This height is h minus 1, suppose, and this height is h minus 2. Okay. Basically, okay, let me give you the question where my question is saying that I want to have an AVL tree such that this left side has the highest number of node. Okay, highest or the maximum number of node, and right side has the minimum number of nodes, minimum nodes. Okay, and that should be done recursively. So maybe, for example, if I just tell you, let's suppose that okay, this left side should be having the maximum nodes. So let me write maximum nodes. Left side should be having the maximum nodes, and right side should be having the minimum nodes. Let's suppose only for root I want it, and for other nodes maybe I don't want it. Okay, but automatically it will be okay, I want to have the minimum number of nodes on the right side. Okay. For only roots, let's suppose I want the maximum number of nodes here and minimum number of nodes here. So how you will be calculating? Let's suppose the height here is maybe let's suppose anything, maybe 4. Okay, height here is 4. Then the maximum number of nodes, if you want to have the maximum number of nodes here, then height should be what? It should be 3. If you want to have minimum number of nodes here, then height should be here 2, right? Because with height 2 also you can have ultimately height 4. So maximum number of nodes with height 3 will be what is the answer? Okay, maximum number of nodes with height 3 will be 15, and minimum number of nodes with height 2 will be 4. So you will be picking 4 and 15 here, right? So you will say the maximum number of nodes you can have 15 here, and here you will be having 4 here, and then ultimately you will be having 20 nodes, 20 nodes in such AVL tree. See, 20 is not even any, okay, here for by coincidence this is 20, but anyway for height 4, this is 12, this is 31, right? But I am having 20, which is basically in between 12 and 31. Why it is in between 12 and 31? Because the way I am constructing it, I am saying that okay, here I want to have the with this height 3 I want to have the maximum number of nodes. With this height 4 I want to, with this height 2 I want to have the minimum number of nodes. So if I want to do it, then I can do it basically, and then the final answer will be 20 nodes, right? So if you want to do it, you can have any number of variations also. Okay. So Rohit is asking how to delete. Rohit, this will be a long procedure if I tell you. So I just suggest you to just look at your notes, because it is just a long procedure that I told you that how to delete in binary search tree. Okay. So let me know if that is clear to everyone. That see, you want the minimum everywhere. If you want to have the minimum in this complete tree, then you want to have the minimum at this here, at this point, and you want to have the minimum at this point. So that's why I'm saying this recursively want to have minimum. Recursively means that you will be using the same formula that you used for this height edge. If you have used nh for the height edge, then you will be using the same thing for other height, which means for the height h minus 2 or for the height h minus 1. I hope that is clear to everyone. Let me know. Okay. Cool. Actually, deletion in the binary search tree not that tough. It is just easy. If you want to delete it, then what do you think? Which node will be taking its position? So I think if this is just one child, then it is very easy. It will be taking its own its position. If there are, let's suppose, two child, if you want to delete some internal node and there are two child, then which will be taking? So see here, the node which is basically I will tell you one thing. I think after that it will be more clear. I will tell you telling you that the BST in order is sorted. BST in order is sorted. So which node should be taking? If there are two nodes here, if there are two subtrees basically here, then which node should be taking its? If you want to delete it, then which node should be taking its position? You need to find either in the left subtree either the rightmost, or in the right subtree either the leftmost, right? Okay, and then you will be swapping it. Then once you swap it, then you just delete it. That's all. Right? Very easy. You just need to swap these two, and then once you swap it, then you can just delete it. I mean, then you can just delete the leaf one. Okay, cool. Now let's solve this question. What this before that, let me know if there is any doubt in those two questions. Okay, let's solve this question. This question is quite interesting one. Very easy question, but it is interesting also at the same time. So what this question is saying, a program a program takes as input a balanced binary search tree with n leaf nodes. Okay, number of leaf nodes are given as n, and they are saying balanced binary search tree, right? I mean, it need not to be AVL tree. They are saying balanced binary search tree. So a balancing condition need not to be the AVL balancing. Okay, balanced binary search tree means that it is completely balanced, right? Okay, I mean, yeah, plus one minus one does not matter, but generally they mean that it is completely balanced, something like this. Okay, AVL is having its own balancing conditions, which means the balance factor could be minus 1, 1 and 0. But generally, if they are saying the balance minus such tree, then they mean the balance factor is 0 everywhere. Okay, generally, although it does not matter for this question also, but I am just telling you. So if there are n leaf nodes, then you can divide. If I just ask you, what are the number of leaf nodes here in this left part? What are the number of leaf nodes here in the right part? Then approximately n by 2 n by. Okay, not approximately. It is n by 2 n by 2, right? If there are n leaf nodes, if this total is n, number of leaf nodes only. If the total is n, then these will be n by 2. These will be n by 2. Anyway, what they are saying, that if there are n leaf nodes and they want to compute a function gx such that gx is, okay, the cost of computing gx is this much. Yeah, this is very interesting. Let me go to the next page and let me tell you that what they are trying to ask. See, they are saying that the cost of, they want to compute a function gx at each node, right? At each node x. So if whatever tree you have, at every point in time they want to compute the gx. right? And gx is the cost of computing gx is basically at any node x is the number of leaf nodes in the left subtree of x and number of leaf nodes in the right subtree of x, and you will take the minimum of it, right? So tell me, what is the cost of computing gx at root, if x is root basically, right? So you will say minimum number of nodes in the left subtree of x, which means these are the n by 2, or the right subtree. I mean, you will take the minimum of n by 2 and n by 2. You will be getting n by 2 here, right? Now the important point which almost all of the students miss is basically this, that gx is the cost of computing. Gx is not this function whichever is given to you. It is not gx, right? I don't even know what is the gx. There is some gx that they want to calculate. I don't even know what is the gx, that what they want to calculate. I don't know actually, to be honest, because that is not given in the question. That's why I do not know what is a gx. All I know that the cost of computing gx is something which is this one, right? This is the cost of computing gx. That's all I know. What is gx? I don't know. So I don't even worry about it, because they're asking what step time complexity that this program take if you want to compute if you want to compute gx for every node, right? For each node, if you want to compute gx for each node, then what will be your total time complexity here? So let me just explain the question again, maybe you will get to understand. See, this is the gx which is given to us. Now they're saying you want to calculate gx at this node, 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 everywhere you want to calculate the gx, right? And for each node you want to calculate gx, and then there will be some cost associated with this node, there will be some cost for this node, there will be some cost for this node. Then finally what you will be doing, you will be adding all the cost, and then that's how you will be finding the cost. Now what is the gx? I don't know actually. Okay, so let's not worry about it. I know that cost of computing this gx is minimum of number of leaf nodes in left of x and number of leaf nodes in right of x. So here the cost of computing gx is n by 2, because leaf nodes in left of x is n by 2, leaf node in right of x is n by 2, a minimum of both of them is n by 2, right? Similarly, what is the cost of computing gx at this node? At this node, what is gx? I don't know. I just know that what is the cost of this gx. Tell me, what is the cost of gx at this particular node? I will say the cost of gx is basically this n by 4. This is the, in the left subtree you have n by 4, in the right subtree also you have n by 4, right? So the cost of computing this gx will be n by 4, because n by 4 is the minimum of n by 4, and n by 4 is n by 4. Similarly here also n by 4, because of the symmetricity. So here the cost of computing gx is n by 2, but here it is n by 4, n by 4. Similarly, it will be n by 8, n by 8, right? Something like this. So basically, if you talk about the root, then you are spending n by 2 cost. Then again you are spending n by 4 plus n by 4, which is basically 2 into n by 4. So that is again actually n by 2 cost. Plus you are spending n by 8 into n by 8 into n by 8 into n by 8, which means 4 into n by 8, which is again n by 2 cost. So basically you are spending n by 2 plus n by 2 plus n by 2. Basically you are spending n by 2 at each level, n by 2 at each level. See, this is the cost which is important, right? This is not the gx itself. You are not counting the minimum number of nodes. Okay, I mean, you do not need to do number of leaf nodes. You do not need to count or something, right? I mean, don't worry about the counting and all. You just have to have the cost in place. So the cost of computing gx is given to us, not the gx. That's where most of the students are getting confused in this question. So n by 2 at each level, and since it is balanced binary search tree, or the balanced binary search tree. Since it is balanced, it need not to be binary search tree. In fact, it can be just a binary tree, because I'm not using any property of binary search tree just to compute this gx maybe. Okay, so the final answer is n by 2 log n. So that's why n log n is the order of this, right? So n log n, in n log n, you have to do it. You cannot do it in lesser than n log n, right? Because at every level you are spending n by 2, and there are log n levels. So that's why n by 2 log n, right? You cannot do it in order of n. So that's why the answer is n log n. Okay, let me know if you have understood this completely. Yeah, cool. let's do this question. This is also very interesting question. As I said, like I will be just picking some nice questions. I will be not be picking some trivial questions here in this class. Reason being is that like I just want to save your time and my time also. I mean, my time is not important because I'm just currently I'm just dedicating my time for the marathons only. So your time is important because gate is very near. Okay. So what they are saying, you are given the posterior traversal P of the binary search tree of n element. So basically they are saying BST post order is given to you. Or n elements are there which are from 1 to n. Interestingly, which are from 1 to n. Okay. I mean, these are the n elements that I have. Now, why I'm saying this is interesting that you have 1 to n numbers, you will get to know. Okay. I mean, there are some not n random numbers. They are actually from the sequence 1 to n. You have to determine the unique binary search tree that the P, okay, you have to determine the unique binary search tree that the P and its post order traversal that has P, okay, posterior traversal, you are given a posterior traversal P of the BST. You have to determine the unique binary search tree that has P as its posterior traversal. Okay, so see, BST posterior traversal is given, then you can easily find out the in order traversal. In order traversal, how you will be finding out? You will say that in order traversal is over sorted, and you know that the numbers are from 1 to n, so that's why you can find out the in order traversal also. Now what they're saying is that, can you find out the BST? And if you can find out the BST, then what should be the time complexity to find out the unique BST that is having the post order traversal, whichever is given to me, right? So the P post order traversal is given to me, and then in order traversal, that is what I by default know. It is basically 1 to n, right? So I will say this is 1, 2, 3 till n. This is the in order traversal, and post order traversal is given to me. Now using these two, I want to calculate the binary search tree, unique binary search tree. I want to draw a unique binary search tree. That is my task, right? Now let's just see if we can do it. Yeah. Hello Basic. So Basic is some user that often comment in our videos. So I don't know his name. If you can just tell me your name also, then it will be good. Cool. So there is some user Basic. So if you can tell me your name, it will be a good idea. Okay. So basically, if you want to calculate the unique binary search tree, then you know that in the post order you write left and then you write right and you have the root, right? This is how the post order looks like. So left, right and root. Now what you want? You want to basically you want to have a unique binary search tree out of these post order in order. So you first need to know the root, wherever is the root, right? So let's suppose root is 5 or 10 or whatever, right? Let's suppose root is 10. Then you will get to understand that okay, this is the root, and then based on this you will go to the in order. You will go to the in order, right? And then wherever is this in order, you will say that okay, whatever here, because here I write in the left, root, right format. So basically for the in order I will say that if I find the root, then whatever is on the left I will say that is basically my left subtree, and whatever is on the right, that is basically my right subtree, right? So that's how I will be finding out. Let me know if that is okay to everyone. Okay, so this is okay, right? So what I will do, I will go to the post order. I will check that what is the root, and then based on the root, I will be dividing. I will go to the in order, and I will be dividing into two parts. So that's my task. I will be drawing the unique binary search tree here. I will be drawing the unique binary search tree here. So what I will do, I will go to the post order P. Whatever is the root, I mean whatever is the last element, I will pick that last element, and then I will go to the in order. I will search that where is this last element in the in order, right? Let's suppose this is the element which is the last element here. So I will make this as a root. I will take this as on the left subtree. I will take this on the right subtree. So I need to do it recursively, right? Now what is the time complexity that it will be taking? See, finding this root, I mean finding the rightmost is not a tough task. I can easily do it, right? Now the thing is that I need to find, let's suppose this is 10. I need to find 10 here in the in order. So if you want to find the 10, since the n order is sorted, you will be taking log n time, right? So let's suppose that that the total time that I'm making in basically drawing the tree, or the in finding the unique binary search tree is Tn, right? If this Tn is total time to finally make the binary search tree with the n nodes using this pre-order and post-order, then what will I do? I will say that okay, if Tn is total time for n nodes, then let's suppose these are the nodes. Okay, these are the nodes which are maybe n by k nodes, and these are the nodes which are how many? It will be n n minus n by k, right? Which is basically you can take kn minus n by k, which is n into k minus 1 by k, right? So it will be k minus 1 into k by k into n nodes. So basically, if you have n by k nodes on this side, right, and then you will be having n into k minus 1 upon k nodes on this side, right? This is 1 minus 1 by k and 1 by k. Yeah, so I think that is correct. So basically, what you need to do, you first need to find the root, and then you will say this Tn is, you need to recursively build here. This Tn is T of n by k, right, plus T of n into k minus 1 by k, right, whatever it is, right? So this will be your cost. But to find this root, you will be taking the extra cost, right? This is the cost to find the root. Cost to find root. Let me know if that is clear to everyone. Is this okay? Yeah, that's where I'm coming. So how to find the right and left subtree? That's where I'm coming. So this is the cost to find the root. Now, if this is 10, then how you will be finding the 10? Maybe since it is sorted, you can do the binary search, right? So you can find this in the log n time definitely, because you can definitely do the binary search. That's the one way, right? So basically, what you need to do, you can find this root in the in order traversal using the log n time. So that's why you can write the log n here. But it is not the optimal way. I mean, log n is good, but it's not the best. See, if it is 10, then one thing I definitely know, that since the in order is sorted, and I want to know the position of 10, right? So one thing was that I can use the binary search here. Another thing is that I do not need to do the binary search, since the numbers are very specific, which are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, like that, right? So I know that 10 is at the 10th position only. I do not need to do anything. 10 will be at this 10th position. So that's why this is just order of 1. I do not need to do anything. This is just order of 1. Okay. So let me know if this thing is clear to everyone, or there is any doubt. Because this is important to understand, that if you like if there is any doubt, you can let me know. But this is important to understand that how we are doing it. Okay. Should I explain this again? So what I'm saying here is that you have the root here, right? I mean, I will tell you more things, but for now let's understand it step by step. You have the root here, and then the root is at rightmost, because this is left, this is right, this is root. And then what you will do, you will basically say that okay, this is root, then I will go to the position wherever this root is, and then that's how I will be finding out that's how I will be finding out basically particular position of the root, right? Okay, so I hope that is fine to everyone. Now what I will do, so with this, what I will do, I will basically be finding out I mean, I will be finding out the complete binary search tree recursively. So let me just tell you that how we are doing it. Okay, so let's have some numbers for example, and then we will be doing it with the code. So maybe I can have some numbers. Maybe let's suppose, okay, I mean, I do not have the post order or the in order with me, so that's why let's suppose that I have this is 4. I mean, I'm just writing, for example, this is 4, this is 3, Okay, this is, let's suppose 2, 1, 3. This is suppose I I will be filling these three numbers. This is 5. Suppose I do have this, or maybe you can have little bigger tree also. But for example, let's suppose I do have this, which you are having 1, 2, 3, 4, 5, 6, 7, right? Now, the post order will be left, right, and root. Okay. So I mean, I am given the post. I have given the post order, which means they are saying that this is left. For the left, I will be writing 3. Okay, this is the left, and then for the right, this is the right, and then root is 4, right? And then I will say, okay, for the left, left, right, and root. This is left, right, and root. So basically, this is the post order that we have, which is 1, 3, 2. Let's suppose they have given me 1, 3, 2, 1, 3, 2, 5, 7, 6, and 4. Right? Let's suppose this is the post order that they have given me. Now, in order is by default. In order is basically, you can say it is sorted, which is 1, 2, 3, 4, 5, 6, 7. Right? This is the in order. Now, suppose I want to make a binary search tree. What will I do? I will take this 4, which is in just order of 1. Okay. I will go in the position of 4, which is also very easy for me. Why? Because I know that position 4 must be at the position 4 only, because I'm having 1, 2, 3, 4, something like this, right? So I will say that okay, 4 is my root, and then I need to make a binary search tree out of 1, 2, 3. I need to make binary search tree out of 5, 6, 7. Let me know if that is clear to everyone. So that's what I want to do. I will do it recursively, but let me know if that is okay. See, the post order is left, right, and root. Right? It was left, root, and right. So I hope that is fine, right? Okay. Let me know if there is any confusion here. Cool. So what will I do now? I will say that, see, I have to do it recursively. I have to find the binary search tree here. I have to find the binary search tree here. So I will be taking the post order of these three just like this, right? I mean, this is the post order of these three, and similarly, this is the post order of these three. So basically, I will know that okay, these are the three numbers here, right? See, I know what will I do? I mean, I know that this is the 4, which means that these are the three numbers here. At least the number of nodes I know, which are 3, right? The number of nodes are 3 here. So basically, to my original input, the whole post order was my original input, but now I want to do it recursively. Now I don't want to mess up with my algorithm, which means I don't want to give this as a whole post order to this sub problem. I mean, this is the sub problem that I have, and this is the sub problem that I have. So basically, I want to solve two sub problems. Now, the in order I don't want to give, or in order I can give, doesn't matter, right? In order I can give, no problem. So post order also I want to give to them. Now, how to give the post order and how to give the in order is basically like this. I know that there are the three elements, right? Because the position is 4. Using this position, I will get to know that what are the number of elements, I mean, on the left. Since these are the three elements, then I'm 100% sure that these three elements I will be going as a post order. So I will be saying that this post order, right? For this, the post order is starting from 1. Okay, I'm starting the indices from 1. That, I mean, starting from 1 to 3. This is the post order. And for this, the post order is a post order. Post order is basically starting from position 4, and since there are three elements only, right? Because this is the position 4, then these are the three elements only. So I will say the post order is 4, starting from position 4, 5, 6, right? 4, 5. I mean, I can actually give the post order differently to them. So I just need to do one thing. I just need to find out the position of root, and based on that, I can say that okay, now my recursively calling, whatever I'm recursively calling, I will say that my post order for this is this, post order for this is this. For example, let me just try writing the code, and then maybe you will get more comfortable that what I'm talking about, right? So let's just see if we can even write the code here. So I hope that is fine. Now let me try writing the code. I will say that make BST. Okay, maybe where can I write? on this page or next page, that's the confusion that I'm having. So let me minimize this again. Okay, so let me write on this page. I mean, I have copied that on the earlier page. Now this is the next page where I have the minimized version. Okay, so now let's just do it step by step. Now I want to make the BST, so I will say make BST is my algorithm. Initially in from my main function, this is my main function, that will be calling this make BST. And initially I have given the post order. Basically I will be calling this make BST, right? And the initially my post order is P, which is given to me. So I will say that C, your post order is P, your starting index. Is this fine if I start the index with 0 or 1? Okay, initially I will say maybe, okay, let me just, I'm writing the pseudo code. So let me just start the index with 1. From 1 to n. This is the start of the post order. Start of post order. This is end of post order. Okay, end of post order. And what else I need to give to the algorithm? I think that is fine, right? Okay, so that's how I will be making my BST. So I will be calling P1n. Cool. Now this is the post order. This is start of post order. There will be end of post order also, right? Now let me do one thing. Let me just try minimizing it so that I can show you everything here only. Okay, so let's just write the code. Now I will say that, okay, I will go to the root, which means I will say that my root is post order of end, whichever is end, it is my root. I mean, I will say that, okay, this is my root now. Now if that's the root, then I will go to the in order and I will say that, okay, this is the position of the root. I mean, whatever is this root, like this is the root, which is 4 actually, right? This is 4. This is the same position in the in order also. So I will say that, okay, in the in order does not matter to me. This is 4 is the position. Now tell me if I want to make the BST, if I want to make the BST for the left subtree, then what are the parameters that I have? What is the start? What is the end? If I want to make the BST for the right subtree, then what are the parameters that I have? What is the start and what is the end? Okay, let me know. So what is the start for the left subtree? I will say this is the start will be the same start that I have, and the end will be just whatever the root position. Okay, this is the same start and the end is this one, right? So if root is 4, then there are 3 elements here. So that's why you will say this is 1, 2, 3. 3 is the end. So you will say maybe that whatever this root index, okay, because that's how I'm dealing with the numbers. This is 1 to n. So the good thing is that it is 1 to n. So if it is 4, then I know that here the numbers are 3 only, right, in the left subtree. So I can easily say that this is root minus 1. I mean, root is basically acting as an index of a root also in the in order, right? I hope that is fine. So for the right subtree, I will say it is P. It is P, and then the start now is root plus 1. Start now is root plus 1, and end is just end. So that's how I will be writing the code. Now you might say that what it is doing and how it is basically linking. Then I have to use the pointers also. So let's suppose let me have this pseudocode in place, and then I will be using a pointer to tell you the exact thing what is happening here. Okay. So this is just a pseudocode that I'm writing. Now let's go to more constructive code where you can actually see that what these things are doing. Now you will say that if you want to write the actual code, let me just try doing it. Let's say there is a node which is struct node, okay, which is definitely having 3 values, which is int val, struct node star left pointer, and struct node start right pointer, right? I mean, there will be a struct node, definitely a right pointer. Cool. So that's how my layout is defined for the struct node. Now let me quickly go to the main function and let me check that what the main function should be doing. So for the main function, I will say that initially I will define the root, the complete root of the tree as null, probably, right? I will say there is a pointer which is pointing to which is a root, let's suppose, which is pointing to, just initially it is null. Now I want my make bst tree such that it finally returns a pointer to the root and I store that in the root. So I want something like this, right, where I will be passing my array which is p, and the start index is 1 and the end index is n. 1 and n are just for my convenience. You can write 0 or n minus 1 if you really want to write the code, okay? So this is how the main function is doing. And then finally this make bst should be returning me struct node pointer, right, which is pointing to the root node. So basically what I expect my make bst to return is, basically once you have the bst in place, I want my bst to return the pointer to this, right? I want my bst to return pointer to this make bst to return pointer to this. Let me know till now if things are making sense. Okay. So I will just see that if we can write a code, but before that let me know if you are getting my point. Okay, let me move further then, right? So what I'm saying here is that I want to have some code which can do it, right? Now I mean I can write the whole code, but I will give you a little bit of idea. I mean I will be writing the whole code, but I will be just skipping the obvious thing, maybe. Okay, or maybe I will not be skipping. So anyway, let's just see if we can do it. Now now we are at the make bst. Now the whole idea that how to write this make bst, and then once we write the make bst, then we are done. So here I'm giving the parameters in the make bst which are initial, like these are the p, and this is one. I mean this I'm calling it start as a parameter. I hope you can see my screen, right? And this is end. So let's suppose these are the three parameters which I'm giving to make bst. Now what I need to do, I need to write this make bst in such a way that finally I have my answer in place, right? Cool. So what is this start and end are doing? This start is basically the start of the post order, and this end is end of the post order. Initially I will be calling it one and end because this is the start and end of the post order. Cool. Now let me write this make bst. Do you want to help me, or or you just want me to do all the things? Maybe I can do it, right? Now what you will say, that wherever is your end, okay, wherever is your end, you will just say that your root, okay, I mean should I be calling it root or not? That's the only variable name confusion that I'm having, uh, because this is an integer array, right? This p is an integer array. So let me just call it root value, okay? Maybe let me call it root underscore val, root value, which is int root value, okay? It means that root value, because p is an integer array, so that's why I want to be very sure that how the code should look like. So it will be p of end, which means I am saying that this is the root that I'm having. Now if I have this root, what will I do? As I told you earlier, if I have the root, I will go to the in order and I will say that okay, this is the root that I have. Then I will make see, if this is the root that I have, then what I need to do, I will make this as a root, and then I will be asking for the left and right subtree. So this is the root value that I finally got, right? Then what will I do? I will actually make this as a root, which means I will create a node which till now I'm dealing with the integers, but now I will create a node which is having this root value as a value, right? Root value as a value, and left and right subtree I want to point to something, right? See, I want to have this as a root value and left and right subtree to something. So here I just need a, I mean, I just have to have some node basically, right? I hope that is clear to everyone. Cool. So let me just call it, maybe I can call it create node. Okay. So this is my requirement, and let me just call it a create node. So what I'm doing, I'm just writing the create node code here. Okay. So I'm in create node. I'm just deleting it. It is just left right pointers, just a struct definition that I have defined. So I'm keeping it, but for the next page I'm deleting, right? So I can have the create node. Now you should be having create node here now, right? Which will take the int value, and it is expected to return the struct type pointer. So struct node pointer, struct node pointer. I should have typed it, but that's okay. This is returning the struct node pointer. So it's very easy code. What you will be doing, you will be writing a malloc function, right? I think it is available at every place. So let me just maybe copy that. Okay. So create node or make node, it is very easy function that will look like this. I'm copying it because it looks nice if we are doing it with a typed format instead of I write it, because my handwriting is not so good. So it is good if I can have the type format. Cool. So this is integer that I have. Now this is, let's suppose, a make node or create node that will take the integer and that will finally return struct node or struct t, whatever, right? Struct node, let me write. So that will finally return the struct node type pointer. Okay. So see, this will return the root, which is basically struct node type pointer. This is struct node. I hope that is fine, right? Make node is fine to everyone, or the create node or make node. So I just like the create node, but okay, here it is make node. So make node, I give this root value, and now I actually have the root, right? So I will be saying this is the struct node pointer, and it is pointing to root, right? That's what I want to return. So basically, till now what I did, till now I just have the 4 in place. I made the 4 because of this malloc, okay, which means I have this 4 in place, and then this left and right I made it to null. This left and right I made it to null here, and then I'm saying these two are null. This is null. This is null. And then this root is basically pointing to this, right? Root is just a small box which is pointing to this. I hope you are okay that how does this root look like? Root is just a pointer. Root is not a node. Okay, it is a pointer to a node. It is a pointer. It is having just a small box. If it is a node, then it is having 3 boxes, right? Because node is having 3 boxes, not the pointer. So root is pointing here. So basically, till now my job is done till now, which means till now I have done till this point, which means root I have created, which is pointing this. It is pointing to null. It is pointing to null. Now, ultimately what I don't want this, right? I want to return the root, that is fine, but I don't want to return this root. I want to have some manipulations here. I want to make a binary search tree instead of this null and null. So that's the only requirement that I have to do, right? Otherwise, I'm almost done. Let me know if you are fine with this, that what I have done till now. Okay. So basically, now I have the root, and finally I will be returning that root. That's fine. I mean, return root is fine. Right, return root, let's suppose return root. And since the root is basically, this is the root which is pointing to, this is the root which is pointing to a node which is having 4, right? And this is having null, this is having null, this is having null. See, if you understand this clearly, then you will be able to solve any question. You will not be having any fear, right? So that's why I'm just explaining. Okay. Now, what we need to do, we need to see that, okay, you are done this till this point. Now you need to see that how to assign this. Basically, you will be returning the root, and then finally whatever you are returning, that will be stored in the root. So basically, this root in the main function will also be pointing to this same thing, right? This node. So you just need to set the left and right. So root left you need to set, root left you need to set, and similarly root right also you need to set. right? So basically, if you notice that make BST is a function, I mean, I have not set it yet, but if you notice make BST is a function which is returning a pointer to whatever should be the root given the post order, right? So, so if I say that this should point to whatever this make node, I mean, sorry, this make BST returning. So which means if I call the make BST here, if I call make BST here with the given post order P, and this time the start is, this time the start is from this start, and the end will be just whatever the root index was, root val or whatever it was, root val minus 1, right? Root val minus 1. So basically this will be the end here. Now this will return me a pointer to, it will happen, it happens recursively. So root left will be pointing to, whatever this make BST is returning. So make BST will return the pointer to the root of this left subtree. So basically this will return to the pointer, and similarly this will also return to the pointer, and that's how you can write the code. So basically it is just like this. I mean, in the pseudocode format, it is just like this. You are having the root, you will be calling make BST on the left part using just the indexes which are start and end, and this time will be root minus 1, and similarly here, right? So how much time you are doing? You are basically taking, let's suppose these are the start to root minus 1, which is n minus k nodes. These are the n minus 1 upon n into k nodes, or k minus 1 upon k into n nodes, right? So if this is n minus n upon k nodes, then this is n minus n upon k nodes. So final answer is Tn is equal to, you are just having this pseudocode. They are asking about the time complexity of this pseudocode. This is Tn by k plus T of n minus n by k, which is, you take n common, probably 1 minus 1 by k, right? 1 minus 1 by k in plus, you are not doing anything extra, right? Just to find the root and all. That's why this is order of 1. So finally your time complexity is this. Now let me write this time complexity in little bit separate page. T of n minus n by k plus T of n into I mean n minus n by k, which is n into 1 minus 1 upon k plus order of 1. This is the final time complexity that you are getting. Now isn't it exactly same as, can you tell me? I mean, just forget about it, but isn't this formulation is exactly same as the quick sort, where you divide into n by k and that part, right? So this is exactly same as quick sort, right? I mean, apart from this. So in the quick sort, if you know that there are two cases, if you talk about the best case and if you talk about the worst case, what are those two cases? You will say the two cases are something like this. In the best case, this is n by 2, n by 2. In the best case of the quick sort, this is exactly same as quick sort. So you will be having best and worst case. So this is n by 2, n by 2 plus order of 1. In the worst case, you will be having Tn equal to T of n minus 1, something like this, right? I mean, this partition, you're partitioning, right? You're partitioning here. This partition can have n by 2, n by 2, right? You're partitioning here. This partition can have n by 2, n by 2, or maybe the root is so you're so unlucky that in one partition you are getting 1, in another partition you are getting n minus 1 or n minus 2, something like this, right? If you're so unlucky, then you may also get something like this, which means just like a quick sort, you can solve it. So if you solve this, you will be getting this is 2 Tn by 2 plus order of 1. I mean, let's just solve it for the worst case. So it is 1 plus 1 n times, right? It is order of n or theta of n. So the worst case is order of n or theta of n. So that's how you can calculate, you can solve this question. Is this fine to everyone? Okay. So in the worst case, you just need order of n, because I do not need to do basically do something extra to find out this root, okay, the root position, to calculate that what is start and what is end. To calculate this end, I just have to have root minus 1. But suppose if this is not from 1 to n, which means if I have to actually calculate where this is 4, then I will be taking log n extra, right? Then my time complexity, see here I'm just writing root minus 1, because I know if wherever I'm ending, okay, if this is the root, I do not need to find the position of root, then I can calculate this left partition, right partition very easily, right? But suppose if I actually have to find out the position of root, then it will be taking log n time. Then instead of order of 1, I have to write the log n here in the both the places. So for this particular question, answer is theta of n. This is an extremely nice question. If you understood this, then let me know. Yeah, thank you so much, Rohit. Thank you. Okay, so basically you do not need to worry about that how things are happening in terms of the code. Very honestly, you do not need to worry about it. Maybe for now you are little bit of in the confusion that how this make bst is making the left child something like this, right? I mean, how this left child is basically making, I mean, how this recursively happening. You are maybe in the little bit of confusion, but that's fine. Reason being is that gate is not asking you to write the code. As long as you are able to come up with this idea that okay, you have to have the root, and then you can partition in such a way you do not need to have anything extra. As long as you can map, you can make this pseudocode in your mind, then you can solve this problem. Gate is not asking you to write the code. Cool. So I think, yeah, so that's the answer. So I have taken n by k and n minus n by k. I think in the explanation, Arjun sir has taken k and n minus k, something like this. I mean, if one side is k, another side is n minus k minus 1 or something like this. So that's perfectly fine. I mean, these are basically the theoretical ideas. I mean, nobody knows whether it is in the proportion of n. I mean, it might be n by k or n minus n by k. Nothing wrong with this, and nothing wrong with this also. I mean, you can have this also or this also. Ultimately, it is just a quick sort. Okay. Ultimately, it will be the best and worst case will be just like a quick sort. You can have n by k, n minus n by k, or maybe if you want to have k and then t n minus k minus 1. You cannot solve it like this. You cannot solve it like this. You have to solve for the best and worst case. And intuitively, I know that best case means half-half. Whenever I'm dividing, best case means half-half, and worst case means 1 and n minus 1. So basically, whenever you divide an array or whenever you have something like this tn, then best case means that half-half or maybe in some proportion. Basically, half is not exact, but maybe in 2 by 3, 1 by 3, some proportion should be your best case. And if they're saying it is worst case means it is 1, it is n minus 1, or maybe some constant only here, maybe k and n minus k. These things comes under worst case. Okay, whenever you are dividing, these things comes under best case whenever you are dividing. So that's how it happens. Okay, cool. Now let's move to very interesting question, which is basically finding the range. Okay, finding the range of numbers in a binary search tree. So they are saying that not just find only one number, they want to find numbers between L and H. Okay, so this is what the question is, and they have asked this 2-3 times. So let's just do it very carefully. Let's just make sure that you know that how to search in binary search tree for a given range, not just for a given node. For a given node, you know, for a given range I'm talking about, given range. Okay, whichever it is, maybe L to H, A to B or something. So suppose they are saying that let me know that how many nodes are there within this range. For example, let's suppose if I just give you this as a binary search tree, and if I just ask you, let me know how many nodes are there within let's suppose 8 to maybe 20, then you will say can you tell me how many nodes are there within 8 to 20? Then you will say 9, 12, 14, right? 17 and 20. I mean inclusive. I'm asking inclusive. So you will say that 1, 2, 3, 4, 5, 5 and 15 also, right? 6 nodes are there. 6 nodes. So that's what the query is. So they are saying, given this range, how many nodes are there? So this is my input, right? This is my input. Like they have given me the range. They have given me the binary search tree, whatever it is. Okay. So they have given me this. They have given me this. They have given me this. This is my input. This is what they're asking. Let me know the number of nodes, right? This is my output should be. So this is my task. I want to design an algorithm that can search for the range, not just for the input, and I want to do it very efficiently. Okay. Let's just see if we can do it. I hope the idea is clear. So what this question is asking, this question is saying that suppose we have a balanced binary search tree holding n numbers. We are given two numbers L and H, and that wish to sum up the numbers in T that lie. Okay, they want to sum up. They don't want to print it. They don't want to count it. They want to sum up. They are saying that sum up all the numbers which are between 8 and 20. That's fine. If you can count it, you can sum it, like nothing, right? I mean, if you can count it, you can sum it, you can print it like that, right? So they want to sum all the numbers which are between L and H. Wish to sum up all the numbers between in the T that lie between L and H. Suppose that there are m such numbers. Okay, then what is the time complexity that you will be taking? So that is the question that they have asked. This is very nice question. As you can see, the number of upvotes in the gate overflow, which is 97. Okay, so 97 upvotes is a, I mean, a huge thing, which means the question seems to be quite tough. So let me know if you're ready. Are we ready to solve this question? Let me know. Okay. Okay, let's just start. So before I tell you the explanation, I will tell you one very nice interpretation of in order. Why it is necessary, I will tell you why it is necessary. See, if you want to find out the in order of this particular tree, then you can definitely do it using left, root and right, which means you will be finding the left and then you will be writing a root and then you will be finding for the right. I mean, you can definitely do it. That's one way. But there is another interpretation which says that you can find the n order by the projection. You can sketch all the nodes on the ground and then you can say this is the n order that you are getting. This is the n order, which means G, D, H, B, E, I, A, F, G, J, C. So basically you have to make it proper. I mean, proper in the sense whatever is in the left hand side, you should be making the left hand side only, which means you should not make the diagram in proper, which means this is A, suppose the left hand side is B and right hand side is C. Now this left is D and this right is E. You should not make it like this, okay? Don't make it like this. I mean, it should be proper. If it is on the left, then diagrammatically also make it left, okay? So that if you want to find the n order of this, just square it. This is D, this is B, this is E, A, C. This is the n order. You just square all the nodes on the ground and then you will be getting the n order. This is nice not just to find out the n order but for the other applications also, okay? So let's just see that that how it is helpful. Is this okay to everyone that we can find the n order by just pushing all the nodes just to the ground and then you can find the n order? Okay, so let me ask you, suppose if you want to find out the n order of this, which is 4, let's suppose this is the binary search tree that you are having, okay, and you want to find out the n order of this, okay. Let me make it proper in the sense that I don't want to mess up with left and right. So if it is on the left, then it is on the left, right? Suppose that this is, suppose I want to find n order of this. This is a binary search tree that I'm having. What you will do? You will squash it. This is 1, this is 2, this is 3, this is, okay, see this 3 is on the left, okay, right? This is 4 and then this is 5, this is 6, this is 7. Isn't it sorted? This has to be sorted, right? That has to be sorted. So basically you can definitely find n order like this. Now I have no interest in giving you this particular interpretation just to find the n order, but I want you to derive some more things by the way we are looking the n order, okay? So I will tell you how we are driving the more things. So let me know if that is fine. Now let's suppose I have some numbers. Let's suppose maybe I have the binary search tree, okay? Maybe let's suppose I have some binary search tree. Now the nodes value I don't know, but someone says that can you fill out the nodes value, then I will say yes I can. If let's suppose the numbers are, okay, numbers are this 3 9 5, these are the 1 2 3 4 5 6 7, right? 3 9 5 2 1 4 1 2 3 4 5 6, let's suppose anything 6. Let's suppose these are the numbers given to me. They say that fill these numbers in this binary search tree such that the resultant is binary search tree. Then you will say that okay, I can do it, but there is lot of effort that you need to do, right? I mean, if you want to fill this binary search tree structure with, I mean, the problem is like that the structure is given to you and then you want to just inject, you want to fill this binary search tree with these numbers such that ultimately it is holding the property of binary search tree. So you will say that okay, maybe 4 should come here. You will get confused whether 4 should come here or whatever, right? You might use some algorithm. I'm not saying you cannot use algorithm, but the best idea is to sort it out, because in order you write the in order of it, which is basically the sorting of it, right? This is 1 2 3 4 and then 5, then 6 and then 9, right? You just write the in order of it. As you know that in order must be the squash one. So you just make the reverse mapping. I mean, earlier what I did, earlier I went from here to here, but now I want to do what? I want to do the reverse thing, which means I want to move from here to here, right? That's the only thing that I want to do. You write 1 here, you write 2 here, you write 3 here, you write 4 here, because you just map it, right? Reverse. You write 5 here, you write 6 here, you write 9. So that's how you will be getting the binary search tree with these numbers. I hope that is fine. Just for the human purpose, I hope that is fine. Yeah. So Muhammad Ali is saying there is only one way. Yes, there is only one way, and that is why there is only one way. Why there is only one way? So basically, if a structure is given to you, right? If any structure is given to you, earlier I just gave you some structure. I will be giving you a different structure, but for now, let me just explain you with the same structure only. So suppose some structure is given to you, and then they say that, see, this is the structure that is given to you. Can you find out the binary search tree for this structure? Suppose they say that this is the structure that you have. Then you will say that there is only one way by which you can fill this tree, with the nodes. So why? Because the in order is sorted, and whatever is the sorted, let's suppose A, B, C, D, E, F, then whatever is the sorted, D, E, F, G, right? Then you will just inject it there. So how many ways are there to fill this structure with nodes such that resultant is binary search tree? So my question is that given a structure, number of ways such that, given a basically empty structure, right? A structure means empty structure. Given an empty structure, such that resultant is binary search tree. So you need to find number of ways. How many ways are here? You will say only one way. And there has been a PYQ based on this particular observation. Okay, I will tell you. That's very nice PYQ. So you have only one way because you just need to inject like this. Now suppose that you do not have any requirement that the resultant structure is binary search tree. Then how many ways you have? See, if you do not have any requirement, if there are n nodes, there are n factorial permutations, right? There are n factorial in orders. I mean, there are n factorial permutations that you can have here. Since there are n factorial permutation, each permutation you can fill by just one way, right? So that's why if the resultant is need not to be binary search tree, okay? Given an empty structure, number of ways such that the resultant is binary search tree, then one way. And if they say resultant is just a binary tree, okay? I mean, this is the empty structure that is given to you. Okay, the structure is given to you. You do not have the facility to basically change the structure. Structure is given to you. They just say that it is just a tree. Okay, a binary tree. Then there are n factorial ways. Why? For every combination, you will be just shifting them up, right? So there are n factorial combinations. So that's why there are n factorial ways to basically fill up any empty structure using the such that the final tree is a binary tree, just a random binary tree. Now, my idea is basically to solve that range search query, right? So this is called range search query. Before that, I just wanted to tell you that how does this in order look like. Now tell me, if I want to have some range search, okay? Suppose this is the binary search tree that I'm having. Wherever my range is, right? If I'm looking for some range, wherever my range is, then what will I do? I will say that, see, just a second. Yeah, I will say that since this is sorted, like in order is sorted, so I will say that whatever I'm looking for, that will be basically will be clustered. I mean, if I'm looking for 3 to 5, then this 3 to 5 is this, right? Which means on this flat surface 3 to 5 is looking like this, but here this is 3, this is 5. I mean, I'm just writing the 3 to vertical. So this is basically one circle where I'm interested in, right? Maybe I'm interested in 3, 4, 5. In terms of tree, it is not flat, but in terms of this in order, you will say this is 3 to 5. And then in terms of tree, this you will say that this is 3 to 5, right? I mean, you will say this is 3 to 5. What do I mean by that? Let me just tell you. Let's see. What do I mean by that? Let's suppose this is your binary search tree that you have, and you want to search for some range. Okay, I want to have a range search in binary search tree, and you want to search for some range. You could be having any range. Let me take some range, which is, let's suppose, which is maybe, okay, any range, which is, let's suppose 0 to 4. Let's suppose this is the range that you have. Then you will say that this is 0, this is 0 in the n order, this is 4 in the n order, and everything, since it is sorted, so your range, whatever you are looking for, is in this circle, right? This circle is your answer. This circle is your answer. So why I'm interested in this circle or something, I mean, why I'm explaining you in that way is because I just want to make you clear that there are no two circles, which means if you are having a range search, you cannot say that your range, whatever, if you are looking for 0 to 4, some of the nodes between 0 to 4 is here, some of the nodes between 0 to 4 is here. Is this even possible? No, right? See, if wherever 0 is, wherever 4 is, right, I mean, you will not be making two circles. That's my point, right? I mean, if it is 0 to 4, then it is basically just this one circle, like this, right? If it is anything else, then also there is just one circle. If it is, let's suppose, -2 to 0, then this circle. You cannot make two circles. You cannot say some of the nodes in my range is here, some of the nodes in my range is here. It is not possible, right? Whatever is the highest, you take that. Let's suppose 6 is highest in this case. What is the lowest? You take that, and in between lowest to highest, since everything is sorted, you will be making just one circle. That's my point. There are no two clusters. If you are looking for some range search, there are no two clusters. Every of your node will be in just this one range. I mean, either one circle, either here or wherever it is, right? Doesn't matter, but it will be just one circle. It cannot be two circles. Let me know if this particular thing is clear to everyone. If that is clear, then only we can talk about the other things. So why have explained you that in order projection is because to tell you that there is just one circle. I mean, you will be just looking for the one circle, right? Okay, cool. I hope that is fine to everyone. Now let's just look for some range. Let's suppose I'm looking for -1 to 5. If I'm looking for -1 to 5, then let's just see how algorithmically I need to do it, right? So suppose I'm looking for -1 to 5. Now what will I do? I will go to this root, right? I will go to this root. I will check that, see, this is the root. If this root is in my range, which means between -1 to 5, then I will go to the left also, I will go to the right also, right? I mean, if this 2 is in my range, then I will go to the left of 2, I will go to the right of 2, I will go to both of them, because 2 is in my range, and I know that there are some nodes that 2 is here. There are some nodes which are left of it is in my range. There are some nodes which are right of it in my range, and 2 is anyway in my range, right? So I will make a pseudo code where I will say if it is in my range, I will go left and right both, right? Now I will come to this left. I will say, okay, if it is -1, again it is in my range, right? Doesn't matter if it is a border or not. So even if it is a border, doesn't matter to me. If it is in my range, I will go to left and right both. So here -1 also I will go to left and right both. And then I will say that, okay, for the left, -2 is not in my range. If it is not in my range, then I will check where it is. It is here, right? I mean, if this is -1, this is 5, this is -2 on the number line. So if it is not in my range, which is outside my range, then I will go to right of it. I will go to the right of it because I am looking for the numbers which are right of it. Since there is nothing right of it, I will stop here. And then from this -1 I will go to left and right, and then I will go to 0. It is in my range, then I will accept it. It is leaf node, so not a problem. I will go here. This is in my range. Yes, 4 is also in my range. Since 4 is also is in my range, that's why I will say that go to left and right both. If it is in my range, I will go to both left and right. Then 3 is leaf. I will say that, okay, this is in my range. I will take it, and then I will go to this 6. Since 6 is outside my range, I will stop. So basically, that's how I'm finding out the all the nodes which is between -1 to 5. Cool. Now let's just understand this more carefully. Suppose I have this binary search tree, this big binary search tree, and I want to have the nodes which are, let's suppose, in some range, which are suppose 11 to uh, 11 to, let's suppose, 26. Okay, suppose this is the range which I am looking for, 11 to 26. I will go to 15. If something is in my range, I will go to left and right both. I will go to left of this, I will go to right of this. Okay, so I will go to left of this 7. So from this 15, I will go to left, I will also go to the right. Now I will come to this left. This 7 is not in my range, but 7 is here. Since 7 is here, I will go to right of it, right? And then I will be finding my range. So I will go to right of it. I will not go to left of it, right? So I will only go to right of it. So for the 7, I will only go to the right of it. Then this 12 is in my range, I will go to left also, right also, right? Then is 9. This 9 is in my range, I will, this is a leaf, I will accept, okay? So basically, this left part is done. On this right part, I will say that, okay, this 24 is in my range, that's why I will go to left also, I will go to right also. Now on the left, it is in my range, I will go to left also, right also. On the right, this is not in my range, right? 27 is here, so I will go to the left only, right? I will go to the left only. I will say that, okay, this is the leaf that I got, which is 25. So this is the leaf, I will accept it. Now, what are the nodes that I have? I have between this 11 to 26, maybe I will say that, okay, I have from this 9 to 25. These are the nodes which I have. So how I'm finding out? I'm either going to left or maybe right or maybe to both, right? So that's how I'm doing it. Now, let's look at more carefully that what I'm doing, right? So at every point in time, I'm asking it, are you in my range? For every node, I'm asking that, are you in my range? Either this will say that yes, I'm in your range, or it will say no, I'm not in your range, right? That's the only two answers that it is giving to me. Now, suppose if I ask 15, then it will say that I'm in your range. Then I will go to left and right both. If it is not in my range, then let me just call it outside node or the border node or maybe something, right? Okay, let me just call it outside node. Outside node. This is not in my range, so I'm calling it outside node. Similarly, if it is not in my range, I will go to one of the position, maybe left or right, something like this, right? Okay. So here also I will be here I have 24. Then here I will say it is in my range, left, right, both. But this is not in my range, so I will call it outside node. Outside node. This is not in my range, I'm calling outside node. If something is in my range, let me just call it range node. This is a range node. Okay, this is the range node, this is the range node, and so on, right? These are the range nodes, these are range node, like that, right? So basically what I want to tell you is that you are going like this, and that at every level, you are doing what? There are, I mean, there are two nodes that that are on the border basically. I mean, what I mean to say is this: basically, you are traversing like this, and then this is the border, on the border. I mean, this is the structure that you are following. So you finally, let me just tell you that you finally actually have this structure. I mean, these are the nodes that you are looking, that you are actually traversing, right? So these are the nodes that you are traversing finally. So the, like, what are the nodes which I'm not traversing? I have actually deleted them. So which means this is the total tree, but from this tree only these are the nodes you are traversing. So this node, this node, this node, this node, this node, and these nodes also, right? This node, something like this. So basically, if you look at the outer surface, I mean the surface, your surface is looking like this. Is looking like this, and then from here, something like this, right? This is your surface. But if you just look at the outer, I mean at each level, just look at it, then you will be just having two nodes, right? I mean, these are called border nodes. So basically, this node and this node, this node and this node. So you are at each level, you are having some border node, which means that, see, whatever your structure is, you will be having some border node, and within that there are many nodes. That's fine. But whatever your structure is, you will be having at each level, you will be having, let's suppose your structure is this. Okay, this is your structure. In between there could be some multiple nodes, that's okay. But at every level there will be only two border nodes, right? This border, this border, this border. Now this border node so happens that, see, these are the border nodes here, right? Border means that these are just coming at my surface level, right? This is on the surface, 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 on the surface. These are the internal things which I am not marking currently. So these are the border nodes that I have, and the internal nodes also I have, but I am not marking correctly currently. I will tell you the reason why. But let me know if this is fine till this point. Now what I'm now we are almost done with the algorithm. Now what I'm saying here is that, see, these are the two border nodes always. Obviously, there cannot be more than two. Whatever structure you have, there cannot be more than two, right? I mean, internally there can be many, but on the border there can be just two. This one, this one, this one, this one. That's all. So whatever structure you have, you will be having just only two border node. Now this border node is sometimes outside your range, or this border node. This is, see, this is also a border node. 7 is also border node. 24 is also border node. But sometimes it could be the outside range. Sometimes it could be within the range, right? Could be outside, could be within. Is this okay to everyone? Now, but there are, at every level there are border nodes. Could be that border node outside, could be the within node. So at least you are visiting two edge nodes, because at every height you are visiting two nodes which are border nodes. extra I might be visiting, that's okay. I mean extra, these are the extra, but 2H nodes you are definitely visiting. Let me know if that is fine. Whatever structure you get finally, right, you are visiting 2H nodes. I mean there might be in the two best case there might be H nodes also, but let's not worry about this number H or 2H. So this 2H nodes, let me just call it border nodes. Now these border nodes, okay, just a second. Now these border nodes could be your range nodes, could be the outside node, that's okay, but these are the border nodes which are 2H. So you are definitely visiting how many nodes? 2H nodes plus you are also visiting these internal nodes. And how many these internal nodes could be? These internal nodes are, let's suppose these are the, in the range you have M nodes, the range you are looking for is L to H. In this M nodes you have, so basically you are basically visiting M nodes also, right? 2H plus M nodes you are visiting. Now in the range, I mean in the range you have total M nodes, and on the border you have 2H nodes, but sometimes the border nodes also are the range nodes, right? See what I'm saying here is that I hope this 2H number is fine to everyone. Okay, so cool. Let me just explain this again. See what I'm saying, that 2H node you are definitely visiting plus something extra you are visiting, right? Which are these ones. These ones you are also visiting. So these ones could be maximum M. If every of the border node is outside node, then these ones could be maximum M. So basically whatever you are extra visiting, the total nodes that you anyway have to visit is at least M, because M is the total number of nodes in the range. So this is 2H plus M. Now from this M, these are the total nodes, total range nodes you have, total range nodes. From this end M, you might be having something on the border also, but that is fine. Okay, I mean doesn't matter if you added M one more time or something like this. So you might be having from this M. See, these are the this is the node which I have counted in M also, in 2H also, because I'm saying this is a range node and this is also on the border. So if the border node is in range node, then I'm counting it twice, but that's fine. This counting twice or thrice does not matter. 2M, 3M does not matter. These are just constant. At most I'm counting it twice. So that is how basically you are calculating your range. Now let me just give you one more example. Let's suppose you are looking for a range which is, suppose which is happen to be 14 to 17. Then you will say that okay, 15 is in my range, I will go to left and right both, I will go to left also, I will go to right also. Then you will say that okay, the 7 is not in my range, I will only go to the right, I will only go to the right. 12 is not in my range, 12 is here, I will only go to the right. And similarly 14 is in my range, so okay, this is a leaf node, I will accept it. This 24 is not in my range, I will go to the left of it, I will go to only the left. And then this 20 is not in my range, I will go to the left of it. Okay, and then this 17 is my range, I will say that's okay. So basically these all are also happens to be outside node. Every border, these are the border nodes, right? And every border happens to be outside node. You are just looking for this narrow range which is 14 to 17, which is 14, 15, 17. And just to visit these three numbers, you have to visit whatever the height it is, you have to visit the 2H nodes anyway, right? At every level you have to visit 2H, right? See these two nodes, these are not in your not in your range, still you have to visit them, right? So anyway at every height, whatever narrow or however wide your range is, you have to visit 2H nodes, that's for sure, right? And then you will say that if these are the two H nodes you are visiting, I mean there might be H or 2H, does not matter. Okay, let's not worry about this H or 2H, but I hope the idea is clear. And then you have to visit, see these are the 2H nodes which I am having, these are the 2H nodes, and then you have to also visit the internal nodes. If the internal is more, that's fine, so you have to visit M more nodes. So that's why the time complexity is just order of 2H plus M, that's all, right? I mean you do not have to visit anything extra, just 2H plus M nodes. Okay, just one last example, let me just give you. Suppose you are having some range which is, let's suppose 1 to 29 or 1 to 30 or something, right, like that, right? Then since this is in your range, actually everything is in your range, but anyway, this is in your range, you will go left and right both. This is in your range, you will go left and right both. Everything is in your range, you will go left and right both, right? For every node you will go left and right both. So here the M is too much, that's fine. Earlier the m was 2 less, that's also fine. But anyway, you are anyway visiting at every node, at every level you are visiting 2h, right? You are, see this outside border, just look at the border, don't look at the internal things. Just look at the border. This is this one is border, this one is border, and this one is border, right? Similarly, this one is border, this one is border. So you are anyway visiting 2h nodes plus the internal nodes you are visiting, which can at most be m. So that's why 2h plus m is your time complexity for the range search, right? For the range search in binary search tree, which is, to be honest, which was not easy for me to also explain, but I hope you understood that how we are calculating the range search. So it was one of the trickiest idea that we have actually, I have actually presented to you using some compilation of some Stanford University. So I've just found this explanation in Stanford University. So there is one Stanford University slide. From that only I have taken this slide. Okay, these diagrams I have taken from the Stanford University. Cool. So basically, finally, the time complexity for the range search is order of h plus m, 2h plus or 2h plus m or h plus m, does not matter. So where h is the height, m is the number of nodes in the range. Now let's see what they're saying. They're saying it is balanced binary search tree. Okay. If it is balanced binary search tree, then height is log n. So for them, the answer is order of log n plus the number of nodes that you have in the range is just m. So order of log n plus m is your answer, which means that here if you find out the numbers, then a equal to 0, b will be 1, c equal to 1, and d will be 0, right? From that you can calculate this particular summation that they are looking for. Okay. So I hope you like this. If you really liked it, then just let me know in the comment section once the live streaming is over. Cool. So let's just move to the next question. Okay, this was one of the trickiest idea I wanted to explain here, but now let's just move to the next question. This is the question that we have just solved. Now let's solve this question, which has been asking GATE 2016. This is very nice question, and that can also be solved using the idea of in order projection that I told you, right? Let's just see what they are saying. They are saying the number of ways in which the numbers this can be inserted in an empty binary search tree such that the resultant height is 6. So height of a tree with a single node is 0. Basically, if the resultant height is 6, then the tree has to be skewed, right? I mean, at every node, at every level, you will be having just one node. 0, height is 0, 1, 2, 3, 4, 5, 6, which means you can have 7 nodes here. So this is 1, 2, 3, 4, 5, 6, 7. So the one of the binary search tree that is possible is something like this. One of the binary search tree, right? I'm not saying this is the only binary search tree. I'm saying this is just one of the binary search tree. Okay. Let me know if that is fine to everyone. Now, what they are saying that how many such binary search tree you are having. How many such binary search trees you are having. That's also easy. Why? You will say that you need to have height which is 6. You need to have height 6. So basically, at first sight, it looks like this is one structure which is possible, and this is the another structure which is possible for the height 6. The another structure could be like this. 1, 2, 3, 4, 5, 6, 7, right? Another structure could be like this, where you can say this is 1, this is 2, this is 3, this is 4, this is 5, this is 6, this is 7. Yeah, that is fine. But you can have any structure such that at every level you are just having one node. Then also you can fill it. How? Let me just tell you. Suppose you are having some structure which is like this. This one, this, okay. One, two, three, four, five, six. Suppose you are having this structure. Is this a valid structure? Yeah, definitely. Then can you fill this structure such that the resultant tree is binary search tree? Yes, any structure I can fill. How? See, I need to fill this structure. So I will be just writing the in order, which is 1, 2, 3, 4, 5, 6, 7. So I know that 7 should be mapping to here. So it should be 7. And then this node should be 6 because it is coming something like this, right? And then, okay. You just need to be careful that in the diagram, that how we are writing the diagram, or maybe let me first tell you the conceptually. Suppose this is the structure that you have. So let me first tell you the conceptually, then I will go to the trick that we are using. So suppose this is the structure that we have. Okay, 1, 2, 3, 4, 5, 6, 7. Then my question is that can you fill this structure such that the resultant tree is binary search tree using the numbers 1, 2, 4, 5, 6, 7. So basically you will say yes. How? Let me just tell you. These are the numbers that you have 1, 2, 3, 4, 5, 6, 7. Then can you fill this 7? Yeah. See, this is the place which says that this node is basically greater than all the nodes. I mean, all other nodes are lesser than this, right? So this place has to be filled by 7. This place has to be filled by 7, isn't it? So that's why we will say, okay, 7 is done. Why? Because all other nodes are lesser than this. Then this is saying out of the remaining nodes, to which node you will filling it? You will say that, okay, see, this is the node which says that all other nodes are greater than me. If all other nodes are greater than me, then I has to be 1, right? This is 1, that's why. So you will say that 1 is done. Now from the remaining nodes, you will say that, okay, this is the place which is saying that all other nodes are lesser than me. So I must be 6, right? Now 6 is done. Now you will say that all other nodes are basically greater than me, which means I must be 2. Then this is saying that all other nodes are lesser than me. So this is done. And then if all other nodes are lesser than me, I must be 5. If all other nodes are greater than me, I must be 3. Okay, and then remaining is 4. So that's how you can fill this structure, right? So you can give me any structure, I can fill it, right? Maybe I can use a trick, or maybe I can do it conceptually, it doesn't matter, but I can definitely fill it. So why to do it so much of headache? Can you use a trick? The trick is that you write it. Okay, if you want to fill any VST structure, you write it in the sorted way, so that it will be 7, 6, 5, something like this, right? So maybe actually this representation that I made may not be much clear, so that's why let me make it. Okay, 7. Just to represent it, I am writing something like that, because it is on the left hand side, and since this is on the right hand side, this similarly this is on the left hand side, this, and if there is something on the right hand side of this, writing like this 1, 2, 3, 4, 5, and then if there is something on the left hand side of this, something on the right hand side, right? So let's suppose this is the structure that I want to fill. Now to fill this structure, what you will be doing, you will be writing something like this. You will be writing the in order, right? So you will be writing 1, I mean whatever is the one leftmost will get the 1, you will be writing 1, and then 2, then this should be getting 2, then you will be writing 3, then this should be getting 3, then you will be writing 4, then this should get 4, this should be getting 5, this should be getting 6, this should be getting 6, 7, right? I mean I have just used the projection that I told you, 1, 2, 3, 4, 5, 6. You just need to inject them up, right? And that's how you can fill any structure, not just this structure, right? So basically, given a structure, you can fill it with binary search tree. So how many such structures are possible such that the height is 6? So see, at every level you have a choice whether to go right or to go left, right? So now my question remains that how many such structures are possible, right? So see, at this node you may go left, or maybe you choose to go, I mean you may go right, or maybe you choose to go left. Similarly, here also you may go right, or maybe you will say you can go left. So basically, how many such structures are possible? At every level, right? At every level you have two choices till the second last level, right? Till the second last level, which means till this level you have two choices. So basically these are the six levels, so you have 2 power 6 choices. So these are 2 power 6 skewed trees will be possible, and for every tree you can fill only with one way. Okay, there is only one way to fill every tree, so that's why the 2 power 6 into 1, which is 64, right? Which is 64 binary search tree are possible with the height 6. So 64 is the answer. Now suppose they just say, instead of binary search tree, they just say how many trees are possible, right? Then there are 2 power 6 structure. How many trees are possible with the height 6? Then you will say that 2 power 6 structures are possible. And then every structure can be filled with how many ways? Filled with, if there are 7 numbers, then 7 factorial ways. So that's why this is the answer, which is 2 power 6 is 64 into 7 factorial, whatever it is, right? So if they just ask you the number of binary trees with height 6, okay, then this will be your answer. Let me know if you have understood or not. Cool. Okay, so now let's solve this question. What this question is saying: in a balanced binary search tree with n elements, what is the worst case time of the reporting all elements in range AB? Okay, they are saying balanced binary search tree. I know the answer is m plus h, where h is my height. Since it is balanced binary search tree, that's why h must be log n, and m is the number of elements, and the number of elements they are saying is k, right? So that's why this is k plus log n. So that's why B is the correct answer. Let me know if you have understood this. That question has been asked very recently in GATE 2020. Right? Okay. Yeah, thank you, Rohit. So now let's just solve this question. This is the next question that we want to solve. What they are saying is that suppose that we have numbers between 1 to 100 in binary search tree and want to search for the number 55. Which of the following sequences cannot be sequence of the node examined? So this is one interesting question, and I will tell you that how to solve these kind of questions. So what they are saying that they have 1 to 100 in their binary search tree, and then they want to search 55. Then if you are looking for 55, then which of the following node cannot be possible? Which of the following sequence that cannot come if you are looking for 55? That's what they are saying, right? Okay. So I hope the question is clear to everyone. Okay, let me see if there is any doubt. Cool. So if you have numbers 1 to 100, then what you will be doing? You will be saying that okay, you are looking for 55. Let's suppose you encounter 10. There is not an issue. You initially you can encounter 10. Since you are looking for 55, you will go to the right of it. You will go to right of it, right? Because you are looking for number 55. Now that is for sure that whatever I am having here, must be now whatever I should be getting must be greater than 10, because I made a choice to go right of 10, right? See, first I encounter 10, that's not an issue, but then I must go on right of it because I'm looking for 55. Then I should be basically encountering more than 10. If I encounter anything which is less than 10, then it is not a possible sequence. So currently I don't have an issue. Okay, so I will go to right of it, and then I encounter 75. Let me know where will I go. I will go to the left of it, right? I will go to the left of it. Now, since I'm going, because I'm looking for 55, I will go to the left of it. Since I'm going to left of it, then I must be having everything lesser than 75. So just check, is everything lesser than 75 also? Yes, everything is lesser than 75. So that's not an issue for me, right? I mean this sequence is valid till this point. Now I will be looking for, I will be, let's suppose I am getting 64. That's also fine, I can get 64, but then I will going left of it, right? So I will going left of it because I'm looking for 55. If I'm going left of it, then everything should be lesser than 64. Let me know if that is the case. Yeah, that is the case, so that's not an issue. Now I've got 43. I can get 43. That's not an issue. But now I will go to right of 43, right? Now I will go to right of 43. Now on the right of 43, I will be getting greater than 43. So just check if everything is greater than 43. Yeah, that's fine. So I can continue. Now I'm getting 60. I can get 60, but I will go to left of the 60. So everything should be lesser than the 60. Then yeah, this is there. Then I can get say 57. Right here I can get 57, and then I will go to the left and I'm getting 55. So that's perfectly fine. I mean this sequence is possible, right? Let me know if you have understood this. This sequence is definitely possible. Now we will see one very nice method to solve these kind of questions. But before that, I just want to know. I just want to explain you a bigger picture that how it is happening. Once you are through with this picture, then you can solve the question very easily. Okay, so I hope you understood that how we are doing this question, right? Now let's just go to the option number 2, which is saying that you are initially getting 90. You can get 90, that's not an issue, but now you will go to left of 90 because you are looking for 55. And then once you say you are going to left of 90, everything should be lesser than 90. Yeah, that is lesser than 90, right? Then you get 12. That's fine, you can get 12, but now you will go to right of it and everything should be greater than 12. Yeah, everything is greater than 12, that's fine. Now they are saying you got 68, you can get 68, but now you will go to left. Now everything should be lesser than 68. Yeah, that is there. Now you will go to 34. Let's suppose you got 34, you encounter 34. Now you will go into right of it and everything should be greater than 34. Yeah, that is greater than 34. Then you will go into 62, you got the 62. Then you will go to left of it, then everything should be lesser than this 62. Then you go to 45, that's fine, and then 55. Yeah, so this sequence is also possible, right? So these two sequences are possible. Now let's just see if the C is possible or not. Okay, and then we will be solving this question with some other method, which is very good method. Now let's just see if C is possible. So you initially encounter 9, that's not a problem, but you want to search for 55, so that's why you will go to the right, and then you encounter 85. That's okay because you can get it. But now you will go to left of 85 and everything you should be getting which should be lesser than 85, which is in fact now you will go to 47, right? And then you will going to right of it, and then it means that everything that you are going to encounter next should be greater than 47 because you are looking for 55, that's why you will go to right of it. So it should be greater than 47, but it is 43 here, which is not possible, right? I mean, you can next encounter 68, that's okay. After 47, you can encounter 68. But then, since you are in this region, you cannot encounter this 43 now. This 43 is not possible. So that's why you will say that if you are going to right of it, because you have to go to right of it because of the 55, so then you cannot encounter, I mean later at the later point in time, you cannot encounter 43, right? So that's why this C is the wrong answer. Let's see this D option and let's see if we are able to do this D option. Okay. So what this D option is saying, initially you are encountering 79, then you are saying you go to left of it. I mean because of 55, right? You are looking for 55. So just keep that in mind that you are looking for 55. Then you go to left of it. You go because of 17, you go to left of it. You encounter this 14. You will say okay, this 14 is good. You can get it because on the left. Now everything now you will go to right of it and everything should be greater than 14. Yeah, that is greater than 14. Then you are encountering 72, that is fine. Now you will go to left of it and everything should be lesser than 72, right? Which is actually the case. Now you will go to 56 and because of it you will go to left of it, right? Everything should be lesser than 56, that is the case. And then you go to 16, then everything should be greater than 16 because you will go to right of it. And then yeah, this sequence is also possible, right? So basically only C sequence is not possible. Now let's just see that if we can do this same question with any good method. Okay, so what will I say here, that if you are getting something, some number, if that is lesser than 55, if you're in the sequence, if you're getting some number which is lesser than 55, then you go to right of it and then you never see a number which is lesser than this number. So what do I mean by that? There are two cases. You get a number which is, let's suppose, x, which is lesser than 55. Okay, in the search you get some number which is x, which is basically lesser than 55. If you're getting some number which is lesser than 55, then you will go to right of it, right? And then here you will be getting all the numbers which are greater than this x. So if a number is lesser than 55, right, then you will go to right of it and the all the numbers that you are going to encounter next should be greater than that x. So what you will do, you will say if you are getting 10, then you will go to right of it and every number should be greater than 10, right? So which means what you can do, you can divide, for example, you can divide this sequence into two parts in such a way that some like you write into two parts, that one part is having numbers which are greater than 55, another part is having numbers which are less than 55. And so let's just divide this into two parts. One is having lesser than 55, which is this one, 10, 43, 10, 43, okay, and then here 75, 64, 60 and 57. So these are the numbers which are I have written in the same sequence. Okay, I have written in the same sequence. These are the numbers which are lesser than 55. These are the numbers which are greater than 55. So interestingly, there is one very important property that we can apply, which is that every number which is lesser than 55, right, which is lesser than 55, should be basically appearing in such a way that the numbers are in the increasing order. So these numbers should be in the increasing order. Why? Because once you get 43, you will be going to write off it, and then you will never see 10, right? You can never ever see 10. So that's why the lesser than 55 number should be in increasing order, and this should be the increasing order, and greater than 55 number, this sequence should be in the decreasing sequence. This is in the decreasing sequence. Why? Because you will go to the left, then you will get lesser only, right? Lesser than 75. And these are already greater than 55. I am taking the numbers which are greater than 55. So you cannot get number which is basically greater than 75 now, right? Because you are going to left of it. So next whatever you are going to encounter, it cannot be greater than 75. So everything should be lesser than 75, right? So basically, if you are encountering 64, now since you are going to left, so that's why everything should be lesser than 64 only. And here it is reverse. If it is 10, then you will go to right of it, and everything should be greater than 55 only. So what you need to do, you divide it into two parts. If this is increasing, this is decreasing, you are fine. Now let's just check the C option. Now the two parts are such that one is 9, another one is 47, another one is 43, and this is 85, 68, 57, right? 55 you can keep anywhere. You can keep at both the places, or none of the places, or does not matter basically. It is end actually. Now just see, a smaller number should be in the increasing order, but that's not the case here, right? This is 947, but this is not in the increasing order. So that's why this sequence is never ever possible, because the smaller number should be in the increasing order, greater numbers should be in the decreasing order. That's fine, but once you get the 47, there is no chance that you can get 43. So that's why C is the wrong answer, right? Now let's just see D. If you divide this into two parts, you will be getting 79, 72, 56. Yeah, that's fine. And then you will be getting here 14, 16, and then 53. This is decreasing, this should be increasing. Yeah, that is the case. This is decreasing and this is increasing. So that's why this sequence is also possible. Definitely this sequence is possible, right? So that's how you can quickly check it. Let me know if you have understood this clearly. Right? Okay, cool. So I hope you understood, right? Now, using this particular idea, we are going to solve this particular question which has been asking GATE 2007. What they're saying, when searching for the key 60 in the binary search tree, nodes containing the values 10, 20, 40, 50, 70, 80, 90 are traversed not necessarily in the order given. Okay, so they are going to traverse these, but they do not know what is the order in which they are going to traverse. Then how many different orders are possible if you want to search for 60? See, what are the numbers which are lesser than 60? This is 10, 20, and 30 is not there. Okay, 40, and then 50. These are the numbers which are lesser than 60. These are the numbers which are greater than 60, which are 70, 80, and 90, right? These numbers should be in the increasing order. That's the only one possible way to come up with these numbers. And these numbers should be in the decreasing order. So that's why the only one possible way for these numbers are 90, 80, and 70, right? This should be in the decreasing order. This should be in the increasing order. Increasing, and this should be in the decreasing. So how many total permutations are possible? Either 1, 2, 3, 4, 5, 6, 7. The 7 factorial, and then these are fixed. This should be in the increasing order, which means 4 factorial, and then this 3 factorial. So that's why this is the answer. And I think if you calculate it, you will be getting 35, I think, right? Okay, I do not have the answer. I think you should be getting 35. As far as I remember answer of this question. So using this method, actually you can find out you can calculate these kind of questions also. Suppose by chance you violate this particular property, or maybe let me just show you that if you just follow this particular property, then what are the sequences that are possible. So what are the sequences that are possible? There are total 35 sequences are possible. For example, you can have 10, 20, 40, 50, right? In between, you can inject 90, 80, 70 anywhere, right? You can say this is 90, this is 80, right? This is one of the sequence that is possible. So let me just, write it more clearly. So this is the one of the ways that is possible. Let me write other ways, okay, which are possible here. So 90, 70, 80, you can write anywhere. Maybe if you want, you can write 90, 70, 80 here also. This is also valid possible. Let me just copy it so that it not be a problem. So yeah, just a second. So if you want, you can write 90, 70, 80 here also. If you want, you can write 90, 70, 80 here also. Okay, these are all valid sequence which are possible. If you want, you can write 90, 70, 80 here. So if you do keep on doing it, there are 35 sequences which are possible, right? You either have to start with 90 or you have to start with 10. That's for sure. Let's suppose in starting you are getting 80. Let's suppose in starting you are getting 80 in the prop sequence. Is this ever possible? If you're looking for 60, you will go to left of it. Then you will never be able to encounter 90, right? So at starting you can never have 80. So they can ask you that what are the starting symbols? What are the starting numbers? Either it can be 10, it can be 90. It can never be other than this. Okay. Let me know if that is clear to everyone. So the smaller than 55 or smaller than 60, sorry, in this case, should be in the increasing order and greater should be in the decreasing order. And that's how more beautifully you can solve this question. This question has got 157 upwards. It means that this question must be very nice. 90, 70, 80 is not possible because once you get 90, then you will go into left of it. You get 70, then you will be going to left of it, and then you cannot get 80 now. You have to get something which is lesser than 70. So Rohit is saying 90, 70, 80. No, that is not possible. Okay. So I hope you understood this. Yeah. So that is one question that we wanted to solve today. Now I want to solve some questions which are very nice, and I mean these are some aptitude kind of questions. But since I have taken more than 2 hours, so I will be solving it in the next session. Maybe I will schedule it today only. Now only at 10 a.m. we are meeting. At 10 a.m. tomorrow we are meeting. Okay. So I will just complete few more questions which are of stack, queue, linked list. These three type of questions are just left. Okay, we have covered hashing, we have covered AVL tree, we have covered heap, right? We have covered AVL tree, we have covered binary search tree, we have covered binary tree or something like this, right? So basically we have covered all of the data structures. Just stack, queue and linked list is remaining. At 10 a.m. sharp we are meeting, so I will just schedule it. Okay. Okay, I have mistakenly written 9070. Oh, sorry, this is 90. I'm sorry about it. This is 908070. Okay. This is basically, okay, I hope you understood, but let me just write it 90, 80, 70. Here also this is 90, 80, 70. Yeah, for probability I can have marathon if you want to. I think, yeah, well, I have decided to have, right? Okay. So let me tell you the schedule that we are going to follow. Okay, sorry. Tomorrow at 10 a.m. we cannot. I think we cannot meet because I mean this is 26th of January, so there may be a flag host. So maybe let's meet it not at 10 a.m. but let's meet in afternoon only. Okay. So tomorrow only we will meeting at afternoon. So for other days maybe I can schedule it for the morning. But tomorrow we can meet at afternoon. So now from my side, the compulsory marathon that I'm going to take is basically for the DS remaining, and then one is for cache, one is for the compulsory. I'm telling you a probability, right? Okay, these three are compulsory which are remaining from cache, from Koa, I will make sure that you understand everything from this cache. I mean, every type of question and the probability. I will be taking the complete marathon, including the random variable and the conditional probability and all. Okay. So this is the order in which we will be doing. First, let me finish the DS tomorrow. In the afternoon we will be finishing it, and then or maybe at 11 a.m. maybe we can have the class at 11 a.m. we can have the class, and then if I have the time, if I can make the slides and all, then I will be taking the class of this cache tomorrow only. Okay, we will see if we can if we can figure it out something, but at 11 a.m. let's just meet. Yeah, thank you so much, Satyam. Just a small request that the way, I mean, we are getting the appreciation is really so much good. Like, we are very much humbled that you people are really liking the sessions, and not just liking the sessions, you are even commenting out so that you are expressing that you are even liking the sessions. So we just request you one thing, that whatever we are teaching, if you are just liking it, then just let us know. I mean, it is good if you let us know. So we have got few comments on the yesterday's marathon. Let me just give you those few comments. So yeah, these are the few comments that we have got. But but it is good if we keep on getting the similar comments in all the marathons. I mean, not on just one or two. So if you're lagging, then only just do it. And I hope you're lagging. So just let us know. Okay. Yeah, we will be conducting probability. Don't worry. So thank you everyone. Thank you so much. Take care. Bye bye. And let's just meet very soon for the general chit chat. Like, I mean, how you people are doing and what should be the strategy for the remaining days and how to keep ourselves calm. So let's just meet for the remaining chit chat in just